Greetings, Calc 3 gang. I am enjoying a rainy afternoon. It's been just a beautiful rainy day today. Hope you guys are staying dry and healthy and doing well. Wanted to dive into the next section with you. We're going to be talking about parametric surfaces. And so I wanted to start by recalling the kinds of things we've already done with parametric equations. So we've been looking at parametric functions of one variable. And so we've seen functions like this: r of t equals some x of t, y of t, and z of t, all the same variable. And we've said that r of t is a vector function with parametric equations, x of t, y of t, z of t. It traces out a space curve. It's important that you realize that the graph of a parametric function of one variable is going to look like a piece of string or a piece of wire stretching in space, something like that maybe. And so, again, we've been looking at parametric functions of one variable. And so, well, being the budding mathematicians that you are, you can't help but be curious. What happens if we look at parametric functions of two variables? And of course, that's the goal for today. And I'll just tell you, parametric functions of two variables trace out surfaces, not just little pieces of string, space curves, but actual surfaces in space. And so let's look at the definition. We'll go right here. So let r of u and v, this is going to be a parametric function of two variables, and you just have three component functions, still x, y, and z, and each component is a function of the two variables u and v. All right, this is still a vector function. The output, when you plug in a point uv, you get out a vector. It's still a parametric function. It's just that now there's two variables involved, two input variables involved instead of just one. And so one of the key things that comes up is before, when we did parametric functions of one variable, we always said, hey, t is between a and b. We gave bounds for t, maybe between 0 and 2 pi. What do we do with the two variables? Well, now, two variables means two space. So instead of getting just bounds t less than a and b, we're going to have a region in the UV plane where you're allowed to pick from. So maybe here's U and here's V, and you can pick this any point you want inside that region, for example. So there's going to be some region in the UV plane that you have to pick your U and V from. That's going to be the domain of this guy. And then when you do this, when you have a parametric function of two variables, you trace out a surface as UV varies throughout D. And so the surface S is called a parametric surface with parametric equations. X is the x component of R, Y is the y component, Z is the Z component. So that's the basic setup. Just one more little picture to try to help us understand. So please keep in mind that because we're working with parametric functions, I still have an x and a y and a z, even if I don't see it. Even, let's just write down an example. I might have an equation like this. R of u and v is u squared v squared u minus v. I don't see any x's or any y's there, but this is playing the role of x. I have x equals u squared, y equals v squared, and z equals u minus v. And so I want you to realize that the graph of these parametric equations is going to make sense in 3 space with our typical Cartesian coordinate system, the x and the y and the z axis. We're going to be able to graph those. And so what's happening is this really cool sort of bridge between two worlds. Over here in this galaxy, so to speak, we have the UV plane. And there's some region D in the UV plane, and you pick a point inside D, and you plug it into R of u and v, and R takes you to a point on the surface over here in the x, y, z coordinate system. And so kind of cool how that works. So I wanted to start out with an example just to illustrate this, and then we're going to switch to Mathematica and play around a little bit. So let's try and parameterize the cylinder x squared plus y squared equals 9, z between 0 and 2 in the first quadrant. And so hopefully you haven't forgotten, right? There's a missing variable, so you just graph this in 2 space. That's just a circle of radius 3 centered at the origin. Stretch it along the missing variable. So I've got this cylinder, and it's stretching up, and it looks like this, right? We want to go only from 0 up to 2, and then we want to be in the first quadrant. So we're going to be something like this is what we get here. All right, so we want to parameterize it. And so, when you see the word cylinder, hopefully you're thinking, hey, cylindrical coordinates, and you should be. I want you to notice something. Notice that r equals 3, which is, r is constant. It's always 3. When you're on this surface in cylindrical coordinates, you're always 3 away from the origin. So that's nice. And so when we're thinking about cylindrical coordinates, we have our r, our theta, and our z. Well, r is constant, so that's good. The only variables are actually going to be theta and z. That's what we need. We just need 2 variables instead of 3. And so now we can actually write down what we want. Let's do it. So we can say, okay, x is going to be typically r cosine theta. Actually, before we write anything, let's go ahead and write down. Let's use cylindrical coordinates. And then we'll say r equals 3 is constant. That way you've got that in the notes. Okay, so now we're going to write down x is r, which is 3 cosine theta. Y is r, which is 3 sine theta. And then in cylindrical coordinates, z is just z. So z is just z. And so I've got my equation now. I can say, well, here's my parametric equation. R of theta and z is 3 cosine theta, 3 sine theta, and then z is just z. And we can actually describe the bounds on everything now. Z, we said from the beginning, we want z to be 0, between 0 and 2, so that's easy. Right? Z's got to be between 0 and 2. We want to be in the first quadrant, so theta is going to swing from here around there, which is just 90 degrees. So theta is between 0 and pi halves. And what I want you to realize is when I've got these bounds on my z and my theta, those are nice, but they actually correspond to a region over in the theta z world. So I'll make theta the horizontal axis and z the vertical axis. We can go between, theta can go from 0 out to pi halves. Z can go between 0 and 2, and so this is 2. So I get this, this region here where you can pick any point that you want in this region. You pick a point here and you plug it into this r. So you pick a pair, theta, z, plug it into r. You get out a point x, y, z, and that point corresponds to a point on our surface. So let's switch to Mathematica, and I'll actually show you how this works, and then we'll look at some fun examples as well. All right, so we got Mathematica up, and here is the piece of the cylinder that we just worked out by hand. And I wanted to show you what happens if you think about this little grid over here being the theta z plane, what we think of as the UV plane. So I'm going to think about theta is my horizontal axis and z is my vertical axis. Just ignore the a there, please. And so if I drag this dot around, I'm picking different thetas and z's, and you can see that everywhere I pick a pair, theta z in the theta z plane, that corresponds to a point here on my cylinder. And so that's what's really fun about this, is you can actually trace out the cylinder just by picking points in a rectangle like that. So that's the whole point of parametric surfaces of 2 variables, and we're going to learn to do some fun things with them. But just to reiterate one more time, when I pick a point theta z in the theta z plane, my parametric equation translates that to a point in 3 space on my surface that I've parameterized. So really cool correspondence here between the points. All right, so that's the idea. I wanted to scroll down and just show you some fun parametric surfaces just for fun. We haven't had a lot of fun since we've gone online, so let's take a moment and have some fun. So here's a couple of surfaces you get. That's a pretty cool surface. Looks like an auger. Could do some fun digging with that. Here's another kind of weird one. These are things that you can't plot if you try to view them as a function of 2 or 3 variables, and yet they're still surfaces. Here's another one. This is cool. You get this weird like sheet that goes through itself. It looks like a flying airplane almost. That's kind of fun. This one didn't turn out very good. It's supposed to be like a cylinder. I don't know what it looks like. I meant to erase it, but oh well. You got to see it. Here is a fun one. It's like a die, like a dice, but it's got kind of inverted sides to it. Kind of random. Again, these are all parametric surfaces. Here's one. This is a donut. It's called a torus. Mathematicians would call this a torus. Kind of cool. Here's another one. I got this off the internet. I found it. Oh yeah, pretty wild. You get this weird looking gear thing, and you can actually control how long this is by changing the different equations. So last one, I don't want to make this drag on too long. Here's like a spiral pipe. So maybe you've seen these vertically like a slide, like a water slide or something, or who knows what. But, all right, so let's stop this video here. And in the next video, we're going to work out a bunch of examples back by hand.